Welcome to the Wigner lecture. As many of you know, and for this is being recorded, and so I just want to go through, and for people who don't know about this already, the Eugene P. Wigner Distinguished Lecture Series in Science, Technology, and Policy was launched in November 2013 to coincide with the 70th anniversary of the first criticality at the graphite reactor. It's organized by our corporate fellows with the goal of invigorating the scientific discovery, spur technological innovation, and initiate productive scientific policy debate. These lectures honor Eugene Wigner, ORNL's patron saint. He was a chemical engineer by training, a physicist by inclination, founder of the field of nuclear engineering, role model for coupling of basic and applied work, which I believe Oak Ridge National Laboratory is sort of its unique signature, is that the translation of basic science to applied. He was a research director of Oak Ridge National Laboratory, then called Clinton Labs from 1946 to 1947, and was a winner of the Nobel Prize in Physics in 1963. Our speaker today is also a Nobel Prize winner. I had a delightful dinner with him and his wife several months ago in New York City. It was actually a dinner to recognize the Blavatnik Award winner, which was our own Sergei Kalinin. And we had a delightful dinner and invited him to come visit the laboratory. So I really want to thank him for being here. He received the Nobel Prize in Chemistry in 2001 for his work on chirally catalyzed oxidation reactions. Barry Sharpless is W.M. Keck Professor of Chemistry at the Scripps Research Institute in California. He received his undergraduate education from Dartmouth College and PhD in chemistry from Stanford University. He did postdoctoral research at Stanford and Harvard. He held faculty positions at MIT and Stanford before joining the Scripps Research Institute in 1990, where his goal has always been to invent better ways for chemists to do chemistry. In 1992, his lab became the first academic lab to use robotics for running chemical reactions. He and his colleagues and students have discovered and developed many widely used catalytic oxidation processes. His work has led to numerous advances in drug discovery, polymer chemistry, and material science. Professor Sharpless began his exploration of what he calls click chemistry in 1998. He has defined click chemistry as a group of reactions that must be modular, wide in scope, give very high yields, generate only inoffensive byproducts that can be removed by non-chromatographic methods and be stereospecific. Earlier this year, he received the Priestley Medal, the American Chemical Society's highest honor in recognition of his invention of catalytic asymmetric oxidation methods, the concept of click chemistry, and the development of the copper-catalyzed version of the azide acetylene cycloaddition reaction. In addition to the Priestley Medal and his Nobel Prize, he has received many other prestigious awards. I would encourage you to go to his website and see his two-page CV, which is essentially a listing of all his awards and recognitions. He holds 7 honorary doctorates and was elected a member of the National Academy of Sciences in 1985. His lecture today is titled New Developments in Click Chemistry. Please join me in welcoming Barry Sharpless.
Thank you, Thomas, for a nice introduction, and I feel welcome here, and I'm glad to be here with my son-in-law, John Graff, who's back there in the blue shirt, and he comes into this talk a little bit. Actually, he helped me once, and I find a nice occasion to talk about it here. I'm talking today about, I thought something else, but then things don't always go according to schedule, and you can't sometimes talk about things for IP reasons, or not that they worry me too much, but you got to respect them for your institute. And so I'll talk about something exciting. I think it could help you, because we all need to make bonds to things, not just figuratively, literally make covalent bonds to between separate entities, and that's the hardest bond to make. If you make bonds inside of a structure by already being attached, that's not so impressive. You're already in the same room together. But making bonds to separate entities is something I'd like to tell you today. I think we've been forced to notice there's a new, there's something missing in the best reactions we have, and that is they're not good enough. 99% yield is not good enough, even though I did that for most of my life, and I was thrilled by 99 or 95% yield. I want to try to explain to you why that's true, and maybe it can help you. I see a lot of times you're down at a ridiculous scale trying to connect things together or see how they'll react to each other. And if you knew you could always make a bond without any question, then I think it might be useful to you. Just as it must be if you're well, let's get into it and see what you can make of it. Okay, this is my sort of hyperbole statement, which it comes from a football coach, Vince Lombardi, who had polio as a child, and he loved sports, but he never played them. And he was so thrilled by winning, and Green Bay Packers were his team. And winning isn't everything, it's the only thing. Well, I like this paraphrase here. We have reactivity isn't everything, it's the only thing. And I'll try to tell you what I think that connotes to me. And this is a slide I saw back in 1968 at an ACS meeting where this very great thinker, he was at Caltech most of his life, and then he went to Chevron, and he was an inspiration to them. He's George Hammond, physical chemist, and he said the most fundamental and lasting objective of synthesis is not production of new compounds, but the production of properties. It really doesn't matter the compounds are sort of irrelevant. There's so many of them that are little, and there's so many that could do the same thing even. What's really we need is properties, functions. They could think of medicines, or you could think of electronic parts. It's all about the functions. And people will say, oh, it couldn't work. But you don't know until you screen it for the function. So really what synthesis needs to be against, and really close hugging, is all these legs which lead up to screens for function. And it's artificial to make total synthesis of natural products, for example. It's probably one of the biggest sidelines that ever sort of led us low in terms of our ability to make an influence on helping society, we synthetic chemists. What is click chemistry? Well, I'm sorry for the wordiness of these slides, but it's M.G. Finn, my colleague for years and former student years ago, but he's a professor at Georgia Tech, and he said this about it. It started back in late 90s. Its architectural endeavors, function and form are intimately connected. If the function of molecules that matters most, and the creation of new function is the goal of honest chemical research, unless it's purely academic. Without the vast potential pool of structures, there must be many, within it, there must be many compounds that would answer the question of the function you need. They have the desired function, but how do you find them? How do you find these needles in a haystack of a vast number? There's 10 to the 63 possible small molecules that could be drugs. Regina Bohacek came up with that number back in the late 70s, and it's kind of sobering number because it's more that there's not enough to make one of every example. With the visible universe, there's 10 to the 80th Daltons, protons, and there's not enough mass out there to make one example of all these small drug analogs. So we're never going to come anywhere near making even a nothing number of them. So why not make the ones that work? So to a unique extent, in the sciences, synthesis, organic type, or you could be inorganic polymers, it doesn't matter. It's making bonds of useful molecules is our focus as more than any other of the sciences. We're just here to serve. We're here to make bonds, make functions by making bonds, okay? Not just make bonds. And we don't have any, that's why we're the central science, not because we're important in terms of the theology of scientific disciplines. That's sort of irrelevant anyway. I always find the Earth we should be in an ecology department. It includes physics, everything. It's all about the organisms and the ecology. We serve life, whether we know it or not, and whether we want to or not. We're just part of it, and it's hard to tell what we can do for it, frankly. I don't know. Maybe we can do something more globally, like prevent the sun from eating us someday. But it's going to do that, according to the physics. This is to give you a quick look of what when you find something, you think it's important. You don't know it's important until somebody else knows it's important. I mean, you can't tell people why your own work is important. You should avoid that at all costs. I mean, we all do it. You can't help it. We're insecure about that. But when it's important, it comes to you as a surprise. Like, I suddenly looked at the journals and I see this kit coming from a company, ClickIt it's called, and two professors at Harvard, I have their slide coming up, but Salick is one of them. They developed the method to use click chemistry. The best part of click was copper QAC reaction. So you're going to see this now. What's going to happen here is that for 30 or 40 years, the literature has BRDU. BRDU was an antibody made to bind to DNA when DNA had an intruder in it. And this is, if there's a methyl here, that's thymidine. And so if you put this bromo in, it'll substitute for thymidine in the backbone of the DNA. And then you can see that organism, that cell, had replicated that day, because you'll be able to see the antibody grabs one of the chains. But you can't do it well. Let's see how it works, and then we'll talk more about it. Okay, so it goes in, gets incorporated into the DNA as if it were thymidine, and then the antibody has fluorescent tags on it, so you can see it, and it's it's raised against this bromo DNA, but it can't bind to DNA itself. They're so invisible, these little bromines inside, that it has to just have it slightly digested. And this comes, the acid and stuff is used, it gets eaten by, chewed apart. It's pretty ugly. The cell gets chewed up too. But this is the way they would find that the cell had replicated. Because if you get an old new strand of DNA on one side, that means you've done the life thing. You've replicated yourself. Now, it binds and sticks. Okay, so it was popular because it was non-radioactive and other reasons. But then came along this kit, which was designed on our copper reaction along with Mitchison and Salick, and we put in the acetylene. This is the key reactant that is always going to react in the copper reaction. It never fails, and so we put those in. Probably get 1 million in each chromosome. These are HeLa cells, human HeLa cells from the famous donor from 70 years ago, and so now they're in there. Now how are we going to get those? Well, it turns out we can go in and just mildly kill the cell and use the copper reaction to do the click reaction. And so here comes the azide. The azide is a little 3-atom strain bridge of atoms that's really hot to do a cycloaddition, but it needs to, there's the click reaction though. And that's why they call the kits ClickIt. And when you click it, the thing, if I went back one, these are not fluorescent actually. These should be dark. But when they when this nitrogen here gets in the ring, by clicking, then the fluorescence is turned on. So only when it reacts does it turn on. And so you light up the DNA. And it's probably used thousands of times a day around the world right now, but people don't even know what it's doing. It doesn't matter, it works. And they light up they check their DNA for, these cells, were these new cells or were these cells here yesterday? And it's a way to track a replication. Here's a picture of it in action. It's basically a way to, you hardly disturb the cell, but you do kill the cell because you need to get it's one of the things that you people love, all these pictures of things that you can see through microscopes. Well, this is just plain old, like what you call it, one of the ones you can see the cells growing through a small layer of them. And then you'll see the movie, cycling here. These are HeLa cells, and unfortunately, they were pulsed with this radioactive, with this ethynyl thing, and then they were captured by having a copper solution with acetylene, with azide go through the solution, and you'll see they light up. This is about 9 minutes, just flowing the copper in, and there are millions in each chromosome, but only, the replication forks are only open. It's about 1% or so get labeled. They light up brightly. So that's a visual proof of having made a bond. Now we come to reactivity, connectivity, and properties. This is what click chemistry is all about. Reactivity has always been what I was passionate about reactivity because I realized early on that somehow intuitively that you couldn't make anything happen unless you had some reaction. If you ever think about different reactions have different inherent probabilities of working. Some are so driven that they blow up if you don't know how to mix them properly, and others are very demure. But I wanted to just say that reactivity is enabling reactions to be made. And then you got the thermodynamics of chemistry and Earth and the universe. You've got to meet those things. So the bonds have to be enough energy in the starting materials to go to the products. But I'm more interested in the reactivity, which is the most difficult thing to get a handle on. And the properties come from the connections. If you just had the right connections and you just made 2 or 3, you could get some miraculous properties. We're starting to have that happen. And the reason I want to tell you about this today is because we found that we can't do our click chemistry dream, which was to make things go together and look for function. We can't do it with a reaction that's only 99%. We need a reaction that's 99.99999%, and we have 2 of them now, and they didn't exist before. That's the weirdest thing of all. We found them since 2002, but that's what I think is most significant lesson for today. So our dreams for click chemistry ran into early troubles. In short, not even the best reactions known in 2001 were good enough for our module connections. You have 2 things together, okay, then you have another of these blue or pink things, the acetylene or azide, and you put another one together. That should be enough for function if you're talking about a drug molecule or something. But we weren't getting enough reliability in the reactions we used, which were the great reactions, epoxide openings, the ones that existed had been coming to us from Germany mainly over 100 years. And 6 of those I chose the best. But none of those reactions was anywhere near good enough for this idea in solution to make compounds perfectly. Okay, so we needed far better reactions than we had. And for example, something like a perfect reaction. And I apologize here to the physical chemists because it's not a perfect reaction is impossible in terms of statistical mechanics, theories and the laws of statistical mechanics. It makes no sense, a perfect reaction. You only have probabilities you can talk about. as a human and the way our understanding what molecules do. Nevertheless, we needed something near perfect, and it came along in 2002, just dropped in our lap by accident. And then, so the best known reactions we'd chosen, they just always failed by a mile for our click chemistry dreams. What was needed to solve this problem was a truly perfect, and his apologies to the wrongness of the concept, not even wrong aspect of the concept. There were none of these when we started, and then suddenly we had a reaction that delivered every time greater than 99.999% yield each step for up to 500 steps. That's the part that really gets your attention here. I'll show you that now. The copper arrived in 2000. We learned quickly that a perfect reaction, what it can do, is unbelievable. So here we have a young woman from this neck of the woods, I think, Ohio, Tennessee, undergraduate, who was working for Craig Hawker in IBM. And Craig was a big fan of click chemistry, and he's developed tremendous thiolene click chemistry. It's not as perfect as we need for biology, but because the thiols that it uses to make ene connections, that goes perfectly if you don't have any thiols in your material. But nature has thiols, so you can't use it there. Anyway, she's using click chemistry, copper chemistry, and she's just showing off it has a good resistance to trouble. In fact, you can't stop this reaction. That's what I want to say. Yeah. Okay. Now here's an example. I had trouble finding the right slide. I just want to show you the QAC reaction takes copper in some minuscule form, parts per million, really, and it catalyzes the reaction of the blue entities, the azides, with the red entities. You can say these are the males and females, or vice versa. I mean, it's whoever the craziness of the imagery here for gender, but they just go together perfectly, and they make a triazole, and there's no questions asked. So if you just take copper wire, which I can find in many drawers here, and I'm sure at Oak Ridge, you just take copper wire and you coil it up and you suspend it in a scintillation file, and you have nothing there. You could have pickled it a moment before, and as long as it got oxygen on it in the transfer process, there's a layer, invisible layer, until it gets thicker, of cuprous oxide, copper 1 oxide. Copper 1 is the catalyst for QAC, and so it makes its own catalyst, and these ligands actually really make the reaction even more vigorous and robust. So it makes its own house, and pretty soon you start, even though there was nothing in there but water and T-butanol and this acetylene, azide in this acetylene, then it eventually crashes out, and there's probably 10 parts per million copper in these supernatant solution. If I now take the same reaction and I take some blood from somebody, maybe myself, and I centrifuge it to get the red blood cells out, and I run it with human plasma, the reaction goes even faster. So this is something I wanted to mention to Dr. Zachariah and the staff. I'm grateful for Wade's help, and he said you would be interested in this because Strong Inference was written by John Platt, a physical chemist or physicist in 1964 in Science, and I've read several papers around that theme, which I would like to share with you, and I'll get them and send them to you. But I never saw them until I was 65 years old. That's a bit of a mistake, because by then all I could have learned from Strong Inference was largely behind me. But whatever my ability is, it's kind of a strange way of viewing the world. I am by nature doing Strong Inference by birthright. I don't know why, I just do it. And here's an example. For example, what is Strong Inference? Well, what happens when a ridiculous solvent like one's own blood is used is, I think, a nice example of John Platt's Strong Inference. For me, these curious behaviors come naturally, what I call vigorously trying to kill your own latest observation or idea that you're in love with because it's yours and it looks great, but it's your job to kill it as quickly and creatively as possible. No complaints, of course, if it survives. Well, that's what this was about. I mean, imagine if you took years, or somebody else would probably find out that this reaction ran in serum and minestrone soup and anywhere you want, hot springs in Wyoming, or, I mean, it doesn't matter, it's going to go. It's unstoppable. How would you learn something like that in the normal course of having found something? In other words, what is it that makes, that's what strong inference is. You waste years and you may never find it, but if you use strong inference, you can really find some great ideas to try. And they're not going to work most of the time. Almost always they'll not work, but when they do. Okay, now the QAC reaction, this copper catalyzed acetylene azide cycloaddition, this is, it's like think of it as a magic forge, which hammers triazole links anytime, any place, anywhere. And when we were the patent people were arguing with Scripps patent attorney that you couldn't have just anything on the azide and anything on the acetylene, and that was exactly the point. So we went back to Washington, and the examiner asked me, she said, well, how can you have anything? No patent could ever have anything on either side. I said, you see the Washington Monument out there? If I hang an azide off that, one azide, and I spray it with acetylene and copper, I guarantee you I'll get that azide, unless the sun gets it first, you know, and photolyzes it. So it's nice to know that whatever, we don't understand this reaction yet, and people would claim they do, but it doesn't matter, because what we always respect understanding of reactions, so we're looking for answers. But what we need, all we need to know now is that it's unstoppable, and if you know how to run it, and if you just play with it, you'll get it to work in almost every case. You can't, if you can heat it, it always works, but if you're in a biological system, of course you can't use copper freely without toxicity in a real live organism. It's enough to know, though, that we have this one reaction, and when the conditions under which you need to construct bonds become truly horrific, it will be the last reaction standing, like a dreaded alien creature, you know, the thing that doesn't die and keeps coming back in the movies. So we have another reaction. It's much more friendly, and it's also almost perfect. And and then yet another one is coming from China and Shanghai, and that's what I hope to talk about. But the fact is that not having looked for perfect reactions before, I don't know why we can suddenly find them. I like to think that we can find more of these. But anyway, just a few good ones is not bad to have. And so we're trying to go forward with that. And you have all the, you just put an acetylene or an azide on anything. This is a virus particle with 60 handles for putting the azide. You put it on sugars or MRI reagents or drugs, and you can pick up in the biological soup, even at parts per trillion, you can pull out anything. And it's a universal connector in a way, like a USB joint. I think the hardest job for people, us to realize, is that when you join separate molecules, you just have to have a very good reaction, because whatever its rate constant is, you've got the problem of presentation and dilution, and they've got to find each other. So it's by definition the hardest kind of a bond, and this is important that this one works best for that job. If you don't have perfect reaction, you're just trying to make something to test biologically, you'll get, in a few steps, 2 or 3 steps, 5 steps, you'll get a mess. That's what we usually get, but we're willing to crystallize or chromatograph, whatever. I mean, chromatographies just aren't acceptable, I'm sorry. I've done thousands of them, but in this new thing I envision, we're not going to have chromatographies. Okay, QAC reaction and the suffix. I didn't have enough time to tell you about both, but I will tell you in the context of John Graff's contribution about QAC briefly. These two, they have this remarkable property. You can run them in a polymer mode, just serially, in one pot, and you'll get a perfect yield. You can do that with polyethylene, polypropylene, and industrial polymerizations. But don't compare them to this type of reaction, because you cannot do them in minestrone soup. You can't even do them in open to the air. Oxygen is a serious quencher of carbon radicals. So the limits, the polymers taught us the way to get, we needed perfect reactions, but they didn't show the specific way. And here's the world of, we discovered going back in German literature, this was known up till 1927 in a group found in Germany that sulfonyl fluorides were really bizarre and that they were nearly immortal, this type, compared to the benzene derivative. This is very, very touchy molecule, and anybody who knows organic chemistry knows your bottles of tosyl chloride get ugly in a year, and probably sooner down in warmer parts of the world. So this is an example of the time I was most surprised of all my life experiences. Remember I told you I'm sensitive to reactivity. The antennae go up when I see weird reactivity in your paper. I'm reading like crazy through it. I don't see anything until I see this signal comes up. I don't understand that one. And then it's usually some mistake, or it's not a big deal. But it's just the kind of way I find quickly what's interesting about reactivity. Well, this is the time you have to read German to do this, which I have done for years, and I have all the German old literature. But here I got this feeling. I read this paper by Steinkopf from Dresden in the Journal of Practical Chemistry. That's my kind of journal. It can be the sexiest, most theoretically beautiful reaction in the world, but if it's really useful, it deserves to be in the Journal of Practical Chemistry. So what happened was I took aniline. He took aniline. I did this with my own hands because I didn't believe it. I went in the lab. Aniline is, in those days, would be brownish. You could distill it, but if you didn't have nitrogen to protect it, it's going to get brown. But it distills at 184 degrees. That shocked me. I thought aniline would boil lower. By then, it's azeotroped every drop of water out, so it's dry. And you take 45 mils, you get it up to reflux, and then you add 4 mils of phenylsulfonyl fluoride. If you add the chloride, it'll about explode as it goes in the vapor phase. But the fluoride just goes in and it stirs at 184 for 3 hours. It isn't a tracer reaction by the most sensitive LC and GCMSs we've got. And that's so bizarre because you just don't, how can that be? Well, that's what makes this suffix chemistry so perfect, because this will react as fast as the QAC reaction and as reliably if it's in the context of a silicon transfer and a catalyst. It's amazingly fast. In fact, you can exchange, if you're interested. We have a paper which should come out, I hope soon. It's a collaboration with a cyclotron, a company in Shanghai, doing screening of Alzheimer's plaques, and we make things where we have a sulfonyl fluoride or a fluorosulfate in the product, and it's very stable in vivo in the biological system. But if we put it in with F18 generated fresh from the cyclotron, sodium, the anion of F18, and we just have the catalyst for suffix exchange, in 30 seconds or 15 seconds, it's totally exchanged the fluoride. Then you quench the catalyst, and it's bulletproof, just like I showed you before. It's really permanent. And we made hundreds of fancy natural products and drugs with radioactive fluorides, F18s on them. Okay, well, I'm going backwards. And here's my one of my favorite recent postdocs. Suha Lee is from He's now in Sun Yat-sen University. He's the chemist who launched the newest gas. And then we share that with you. We scare people a little bit. The trinity of gases that we love now is SF6 stands alone as enabling us to have a power grid that doesn't fail. And you need UF6 and SF6 if you want to be a world power, right? You need both because you need the F6 to make atomic weapons, but you need the SF6 so that you have a button you can push to set them off. It's really kind of not a funny joke. That's why people don't want to make thorium reactors, I'm told. They don't get the nuclear capability. But it's kind of interesting that calcium fluoride, all the fluorine and fluoride that came in early in history here, and China is so big in it now, it's just impossible not to want to be there. If I had to choose between the US and China, I wouldn't hesitate a minute. I can get all these gases. We get kilos of these gases made for us, and if they work, we're going to have a connection with reality because the gases are made. SF6 is cheap, SO2, F2, the fumigant is cheap. In between is SO, F4, and it's really wonderful. Right now, there's only 2 kilograms of it in the world. One is in our lab, shipped from China, and the other is in Jiajia's lab in Shanghai. But we've got a lot of papers coming out that will make people hopefully want to make that a production gas. This is the reaction, the QAC, the same thing happened with QAC. It was a polymer grade reaction, so people have used it to make polymers. But here, this reaction Jiajia found early, and Sua replicated it, but you take a sulfonyl imido-oxy, this is a nice crystalline compound made directly from the aniline, and now you do a suffix catalyzed transfer to silicon, and you get the polymer, and it forms rapidly at room temperature in N-methylpyrrolidine, and it's almost essentially quantitative, good polydispersity, and the molecular weight is 204,000 approximately. So there's about 600 of these links in it, and it's kind of surprising that it doesn't cross-link or anything. And the way you can see it's pretty perfect is by the NMR. That's the proton NMR of this molecule, and you can see that it's sharp as solution. Seems to be a singular entity. And here's the fluorine NMR. It's a reference, and this is 900 megahertz for proton spectrometer. So it's a good, strong signal, and there's a single peak. And all of these centers, you have to be R, or SSS, which they apparently are, because otherwise we should see kind of zigzag things and isomeric structures. So that's a case where we think the polymer, when it's alive with a catalyst, is just reforming itself constantly and looking for that thermodynamic endpoint where entropy and enthalpy say there's a material out there, go for it. Because if all you have is a reversible reaction, it goes to the side you want, you can get a perfect thing, can't you? Because the thing that prevents these kinds of reactions from having commonality in the world is that most reacting pieces have other friends they're going to react with. And so anytime you have a lesion there, you go quickly away from perfection. Okay. So if we had 99% yield per step for these 660 steps, we'd estimate 0.2% yield at the end here, of which 0.2% out of 100 of a polymer which had the register that we say it should have there. Oop. And this is where the calculations that John Greff helped with, he's good at engineering and math, and LED was his first startup company that he was in. And anyway, here's the 660. To get a yield for this, you have to take the average, the number of reactions to the power. In other words, if you have 660 reactions, you raise 99% yield to that power, and that's how you get the attrition here. But if you have a lot of 9s here, you can sort of intuitively see why it's much better. You're multiplying nothing times nothing. You're not going to drop out of the 90s range soon, and that's the way it works out. This is what John sent a couple years ago when we were first talking about this. And okay, here we have 100% yield for 100 steps in a row. So if we get 100 steps in a row and we have 100% yield, well, we need to have this kind of fidelity. This is the log plot of the decay of the right product in the mixture as opposed to all the other products. And it's a 1% cutoff so that you can get a linear line down to the point where they fall to 1%. So both QAC and suffix happen to be so orthogonal, they have so few friends, so few things they can do, that they just go perfectly, and they go out still pegged out here at 100 steps. You'll notice 90% yield has got you down here at 100 steps at 30, I think it's in the 30s. Now, if I were a pharmaceutical company and I was looking for new drugs, if I took that polymer reaction and ablated the functional group, this one and one over here, now I'm in a monomer context. And in a monomer one-off reaction context, these reactions really are perfect. So if I put this on, then I put this element on, and that goes by suffix onto the remaining fluoride quantitatively. Now I'm here, and then I put in AZT, for example, which from India years ago, from a good friend who runs CIPLA. He's a very generous man. He gave me 150 grams of AZT. He was making it then for Africa for free, and he showed how much you can do in this world if you're not trying to make money out of massive amounts of money out of medicines, and that's the evil culture we have in medicine. And hopefully cook chemistry can break the back of that because you can do this in your own kitchen if you had to. Anyway, here we go. We got a thing. Suppose I told you this was a miracle drug for HIV. Hey, it's imaginable, right? It has it's pretty good size, and you know, it's not hard to do. It's not hard to imagine. And the yield of that would be near 100%. And we can make any compound we make this way, we can make milligrams to kilos of within a week. That's by definition. There is no process chemistry. These are the best reactions we know in this world. Okay, you have to believe that you can get those connectors into the drugs you need. That's turning out to be pretty easy. Another thing we do, we go fishing with this new gas, SOF4, and the old gas. They give these compounds which actually are not totally innocent in a living system. They do interfere, they do something. And what they do is react with proteins. And so we call them, when they're the fluorosulfates that do find a protein, they usually find only 1 or 2 proteins in the whole proteome. So they're very picky. And so my wife said, oh, as soon as I told her that, she said, that's a sleeping beauty. And I said, yeah, it's a really good idea. Because if you boil the enzymes in the proteome, if the enzymes are denatured, you will not react in 100 years with this thing. It's absolutely impossible. But the magic of life's natural conformation, enzymes, and all these electric fields, that undoes the knot that talks to the Sleeping Beauty, and the protein gets grabbed. Now so that's why we think of it as a prince in Sleeping Beauty, and they're permanently connected forever. And then you have it function in the drug department, and I'll show you some of these. Most of the compounds the Sleeping Beauties play the waiting game, and they just wait for the unique prints. And then here's one. This is a tyrosine active site of a protein. I won't name it because it's not published yet, but it just grabs hold of a phenol. And so we have this, and this residue is stable to refluxing sulfuric acid. These diaryl sulfates are permanent entities. And they're beautiful. They have no properties. They have no polarity. They're going to be in drugs of the future. But here's a case where Sleeping Beauty actually grabbed a protein and gave a phenotype in the organism. And here's another one from this human neutrophil elastase. This is from Dennis Wolman's lab at Scripps. And we went fishing here with a difluorosulfonyl fluoride, a very weird creature. But we decided to fish with just about anything we can make. And we found it goes on and stays on. It reacts with the active site serine of this very important metabolome elastase. It's really a lethal type of protein in actual fact. In people that are poisoned with the organisms that throw this out as a weapon, you have to find ways to catch it. And one of the sulfonyl fluorides is still there. The other has been captured by in the triad there with the histidine activating the serine. And this is my group. Mostly it's Jaja's group, and he's the professor now at SIOC. But I have about 5 students in this group, and this is us in Shanghai. And I was thinking I was going to talk about their work today, but so I don't have my other slides for the group. But I mentioned the people as I went along, and I thought maybe the connection of the guaranteed connection at a level of 99.999, that's a message that I wanted to share with you, because only in the last months, because of the breakthrough that they had in Shanghai, is it become clear what we can do. We just make 1,000 libraries that are perfect at a time in screening array and test them in all kinds of assays all over the world, but especially in Shanghai, and we're getting amazing results. And so the idea is that if you have a need to make a link to something, I mean, if you're up on a cliff in the north face of the Eiger, and you better not worry about using any other reaction than the QAC reaction to try to get some bonds to that cliff wall, because you would be foolish, because it would be the last reaction to fail. And so I just needed to tell you this. Before I was afraid to say this because people don't like click chemistry anyway. And then but those who use it, the biologists and material scientists, they like it because it works. That's what I wanted to get. The message is, if you need a link to something, we think you can get it tomorrow if you have the azide and acetylene and the copper. Okay, thanks.
So I think we'll Barry, first of all, once again, thank you for being here and for this wonderful lecture. So I will, there are lots of we, as a organization, we are at a point where we have a lot of new people in the laboratory. The laboratory is growing, lots of unique facilities. Hopefully, you'll get a chance to visit with them. Okay. Now I'm going to expand your statement by saying that we all need to make bonds. So I would like for you to give your perspective on how you would advise us as an institution of smart people to pursue their passion in the work. You talked about making covalent bonds, so I'll let you start with there.
Well, it's a good place to start. I had another set of slides that I got up early this morning and threw those away and started over because it was just too open-ended, and they were about nature's inspiration, and of course the fact that we are nature, so we're doing something we think is our own, but it's hard to tell what we really are responsible for. But nature is the most complex system that we know of in the universe, and it only appears to be on Earth so far. But why is it? It's got some sort of magic in it that we may never understand. But one thing that's clear is its strategy for making function is very simple. 35 building blocks. and they're mixed in, and they get reused because we can't reverse our reactions. Those are what man can do with his hands. We need a reaction because we're not working at the level of the molecules. We're working imaginatively at the blackboard, and then we use statistical mechanics to explain how we actually get something. But nature is somehow intuitively doing all this chemistry, and she just puts the pieces together. There's an enzyme, titin. I think it has 10,000 amino acids, and it's in us, and it's in mice, and it's what our muscle. It's a long protein in muscles that's used to get traction for the other proteins, and it's got repeat units. But 30,000 or 10,000 amino acids, it's a pretty boring job. They put one on, then another one, another one. It goes one at a time. It goes fast, I guess, but when you think about the medium is the message there. In other words, the function comes from making a covalent bond, from something that wasn't connected, and then that's true in DNA too, and it's true in sugar, oligomers, and starches. So the idea is if you can make covalent bonds perfectly, like you can imitate that aspect of nature, and one thing that comes from being able to, what was I going to say? Okay, it'll come back to me. I just think the modular nature of life. If we found life somewhere else, among the other things, the only thing I would never believe there would be a life system without water. I mean, I think water is, the interface of water is life. Oil and water is where life started, I think. And so, okay, but the other thing is modular. If you need something fancy, and it ends up when you make a fancy thing like life system, you end up with chirality. Mm-hmm. It doesn't matter that you have chirality because you can sort it, but it's going to be, say, right-handed or left-handed. And that's something which the system could be exactly, you and me could be somewhere a billion years away on light, on another, it'll be mirror images of us, okay? Everything, nothing changes. In fact, smell, like oil, skin oils, they smell the same, they're flat. So we wouldn't know that we were from, nobody would know, and everything else would be the same, except we needed different refrigerators to eat from, and we'd never be able to get diseases from each other. So it'd be, because we're just mirror image creatures, but otherwise, but the way we know is pretty sneaky. If I'm worried about this other person, I take a mirror image terpene. One is left-handed carvone is spearmint smell. Right-handed is the smell of rye seeds, cumin. And if I know it's spearmint and you smell rye seeds, I know you're from that other place. Because the nose is, your nose is chiral, okay? It's your nose, our nose has a right-handed receptor for that, and the other guys have the left-handed receptor, and they're switched.
Okay, so I had this fascinating conversation with Elias Terhuni, former NIH director, when he was president of the R&D organization at Sanofi. One of the things that he said that stayed with me was that he says that, he had an annual budget of $5 billion, and he says that, he has to go to the board and present this $5 billion budget, knowing that 95% of his experiments are going to fail, okay, because he was not expecting a yield in terms of the various experiments of 5% would be great. So you talked today about 99.999% yield based on the recent work that you and your colleagues are doing. So how is it going to change the field, or how do you expect the field of drug and pharmaceuticals to change?
Well, I don't know. I would like to think we could actually get a drug. We got something promising in cancer that's been through tox and everything, and so I'm hoping that then a big pharma company would come to the professors over there who did it in the biology and they just say, "Can we develop it for you?" That's the traditional way, right? But I think that if a pharma starts using this to look for the function, the point about the biggest problem they have in these libraries, they get thousands or millions of compounds, and they can't even test them for phenotype because they're on solid phase. And so if you get a hit that you're not sure of, well, you can't just take it off and find out what it is or use it because there's none there, really. It's very low level. So to be able to make compounds as they would be in solution and then make grams of them, that right away makes it very attractive for pharma, I would think. So I think they'll jump on this. But I don't know. Oh, what you said about the NIH leader, there's another problem, isn't there? Strong inference, I think, helps an awful lot, but because I'd say 95% of the work that's funded is not worth doing. I mean, we kind of love our own stuff, and we write these things, and we say we're going to do this, and we go 1, 2, 3, and we do it, and we get money again for another year of grant funding in our research. Same game for academics, and you know. If you use strong inference on everything, well, even if I do this really well, does it matter? That's got to be one of the strong inferences for a society that's not rich anymore. The taxes people pay, they're not doing this to be friendly, or they're hoping for medicines or some miracles that help them or their children or their friends, right? Isn't that what we're hoping for? That's why I'm sure you're doing this job. And I mean, we all try to help somebody, but we're not helping them if we just get off on an ivory tower and have angels dancing on the head of a pin.
Well, so this would be a good time to open up the audience.
By the way, my hearing aids, I forgot them at home, so yell at. Okay.
So there's a microphone, so that people who are watching, remotely can hear. Please use the microphone to ask questions.
Hello?
Jeremy, there.
So it's a fascinating talk here. So you said correctly that we can synthesize zillions of those compounds and synthesize every day, but it's finally the properties or the functionality that matters. So how do you think the machine learning and AI, does it captures enough fundamental science as input for the next click chemistry or things? What's your take on it?
The eye?
Yeah.
The artificial intelligence
Yes.
and machine learning.
Oh.
Yeah. So how does it enable your chemistry?
Until last year or so, I heard lectures in China when I was over there for visiting my lab, and there were some meetings we went to, and the man from India, who actually is out of India now, he was so inspiring. I mean, artificial intelligence, I thought was, they can't even drive a car very well, but so that was like an eye-opener for how complex our brains are. But now I'd say I learned that, yeah, artificial intelligence is a very rich field because it takes it teaches itself how it's going to react to something, right? And if it uses our input, it's not going to help us, frankly. I think we already have these strong biases, and we really need something that can do it from the deep data and find a trend, but it'll have a lot of sort of blind alleys too. I think the biggest problem with us, if I could show you about 10 vision distortions where they're famous for showing how we don't see what's really there. We see what our brain wants us to see, and so that's one of the. And we see pictures. Really, we see sort of frames going by, and that shows how slow and how intentional our brain is giving us information. So I don't think we can trust things that are only visual. What I'm saying is that the results of a screen against a system that's up and running, a living system, a very unique kind of dedicated embedded system, that is unambiguous results. And then you can pursue that, and you can take it all the way down to the exact protein that may be getting, but that comes later. I don't need that to make the drug. I can look back later, but I need to keep going down on the activity. The toxicity goes away. Just like everybody who ever made a drug, you got to prove it doesn't hurt somebody, and then of course you always have the surprise of the next generation, like thalidomide and that other drug that gave birth defects in the next generation, you could have any new drug do that, in principle. I mean, there's now covering for some of that by pregnant animal tests, but we never know anything except by function, what the readout is. I mean, the readout of life is what it is. It's a message. It's its own message. It's very hard to say what life is, but we know what it is.
Syed?
What is critical about copper? In the case of QAC, what's the critical about copper, except it's electropositive and it's a transition metal? So,
Yeah.
so can we use another electropositive metal?
Well, people have tried. There are other reactions that are really good. If you only need to do it once, you can, like Bertozzi and others have strained olefins. But the thing that's sort of misleading about saying is, when you get a really high yield, what you're really also saying, and that's where you make a mistake, because most reactions that can give you 99% yield in their own milieu, when you put in other functional groups, like things all over the intermediates we use, amines a lot, they have acids, they have all kinds of functional groups. Those groups have to be irrelevant to keep on this line of perfect reaction. And in fact, they aren't irrelevant for most reactions. Most of us get interference by things. So if you find reactions that have no interference, and the Sulfex reaction is close, it has kind of the sexiest application, I think, and that is the one where it can silently pass everybody by in a life system, but not everybody. It can capture one thing, or only one thing. And that would be a very potent way to have an add-on to these really easy to make scaffolds. I don't know if you want to change, as a chemist, we want to change the parameters. I mean, Peter Schultz said, "Oh, Barry, that's good. I like that copper reaction, but can't use copper. It's toxic." And I said, "Oh, thanks." You know, just all these years later, well, we're still using copper on that reaction, but and I think we have this limited view of things. We all do, and I was amazed that I didn't realize you can't even make one bond and get a pure compound in a context of a drug with all these other functional groups there. You can't even do one with a 99% yield reaction that isn't one of these perfect reactions. You have to purify the thing, or you have to stand on your head a bit, and it's just not something we do well, and people avoid that by doing combi chem with DNA and everything. But it's going to take it's so far removed from what you need to do. I got activity. I want a few milligrams to see if that's the compound. I want a gram to see if it's toxic. I want that this week. That's the way I am. I'm strong inference. I want to go quick. If I can't go quick over the ground, then I can tell you I'm getting ready. And that's what most grant money goes to. I'm getting ready. We don't need to get ready. We need to hit the hot spots.
Barry, I'm sure there are a lot more questions, but to keep you on schedule, I think I'm going to bring this lecture to a close. So we have a small token of appreciation that I would like to give to you. It's heavy, so we can always arrange to be shipped.
Oh, nice. Yeah, it's a good thing to have in your office.
Indeed, something to remind
something
you.
Heavy. Thank you. No, Wigner, I forgot to say it's a real honor to be. Wigner was a giant, obviously, and so many people from that time were amazing. That we got all these great immigrants in this country that they could do our necessary hard things, right?
Indeed. So yeah. Thank you very much, and thank you for a wonderful lecture.
You're welcome. Thanks.